Hey guys, how you doing? This is Coach Scott, Purple Wave Chemistry. Let's move on in Unit 6 and talk about intermolecular forces and dipoles, whatever they may be. We'll see. Right? So, talked a little about states of matter, right? So, the state of a particular piece of matter or stuff depends on one, the temperature that it's at, and pressure, right? And these are on two major factors. One is the strength of the intermolecular forces that hold the molecules together. Right? So that's between two molecules. Right? Boom. Something holding these two atoms and those molecules are now together. Right? So that's the intermolecular forces. The other one is the kinetic energy of the molecules. So molecules have the highest kinetic energy in which state do you think? Well, of course, it would be gases, right? Because those suckers are moving everywhere as much as you could. So intermolecular forces, we've talked about them, right? One is a covalent bond. Now, that's pretty strong. And these things are electrostatic forces where you've got attraction and you've got repulsion that exists between the molecules, right? So the intermolecular forces are between the different atoms, right? So the attractions that are between molecules and between ionic substances, all right, the intermolecular forces are between the different molecules. The intramolecular forces, okay, are these attractions that are holding these compounds together, right? Not between the atoms that make up the compound, all right? So these intermolecular, the bonds are very strong. The forces that are holding the molecules together are not as strong. Okay, so if you look at this demonstration, if we didn't have intermolecular forces, IMFs, then everything would be a gas, and there would be no liquids or solids, and we'd be a gaseous. Well, yeah, you think about that one. So let's think about ways we can change things, right? Intermolecular forces, and let's think about boiling points. So a boiling point is a transition from a liquid to a gas. So to move or make that transition, the molecules that are liquid, they're going to have to break free from the intermolecular forces that are holding them together. All right. So also the kinetic energy of the molecules is proportional to the temperature. As the kinetic energy rises, so does the temperature. So really, the temperature is a measure of the kinetic energy of that compound, right? So the boiling point is the temperature when the molecule's energy overcomes the intermolecular forces that are binding them together. The higher the boiling point of a substance, the stronger the IMF, right? So water will boil at what, 100 degrees C? All right, and it starts boiling away, which is sort of high. So there are four types, I'll write this down, four types of intermolecular forces. One is a dipole-dipole interaction. We'll talk about what a dipole is in a bit. The second is a London dispersion force, right? Call them LDFs. Another one is a hydrogen bonding, which is not really bonding. It's a intermolecular force, but it's pretty strong. The last one is an ion dipole force. Now, the first three of these you can also call the van der Waals forces, which I love that name when I was in college, the van der Waals force. But we're not going to use that term because we don't use it in AP chemistry, because all three of these are van der Waals forces. So, what is a dipole? If you recall from Unit 5, a dipole is a polar molecule. So let's think about what a polar molecule is. I know we've talked about that in a while ago. So a nonpolar covalent compound has a very small difference in electronegativity. Polar covalent compounds or molecule will have a difference of around 0.2 to about 1.6. And of course, an ionic compound is going to have an electronegativity difference, or delta, of about 1.7. So pretty much we're talking a metal and a non-metal, right? So these dipoles, let's look at this example. This is hydrogen fluoride. This is an example of a pretty good polar molecule, or a dipole. So the fluorine end of the molecule is going to have that electron that is sharing much more than the hydrogen end, right? Because of its higher electronegativity. And we put this little symbol in, if you recall. So this is the positive end of the molecule, and this would be the negative end of the molecule, where the electron is hanging out more that is sharing with the hydrogen, right? So that tells us what? That negative end is going to attract the positive end. So look here. These molecules have what we call a permanent dipole, and they're very attracted to each other. So that positive end is attracted to the negative end, and vice versa, vice versa, vice versa. These are very important forces because they're important when the molecules are close to each other. All right. So most of your polar molecules will have this type of intermolecular force. So whenever it's close to each other, they'll be attracted to each other. When the negative end and the negative end they're going to be repulsive, right? So you've got repulsive and negative forces. Repulsive and attractive forces, rather. So another one is this, called a dipole-induced dipole. All right? So this happens when a polar and a nonpolar molecule become close to each other. All right? So when they become close together, the dipole will induce what we call an instantaneous dipole in the nonpolar molecule. All right. So when they come close, the electrons will move toward the positive pole of the dipole molecule, like so. So this instantaneous dipole, these electrons move over there because of that positive end, and it becomes very quickly a dipole. So these interactions are present whenever you have a polar and a nonpolar molecule, right? So these permanent dipoles, right, will induce a temporary or this instantaneous dipole. They're very attractive, or they're always attractive, all right? And the strength of these forces will increase with the magnitude of the dipole on the polar molecule. And the strength also increases with the polarizability, big word, of the nonpolar molecule. So, the polarity of a molecule is measured by what we call the dipole moment, and I think that's a mu in Greek, a little backwards U type thing. So the more polar the molecule, the greater its dipole moment. The more polar the molecule, the stronger the attraction is between the molecules, the higher the boiling point. So if you have a lot of attraction, you're going to have a much higher boiling point. And we like boiling points in Kelvin. We'll use that. So I've got acetonitrile, CH3CN, right? Compound. It's got a molecular weight of 41 AMU, atomic mass units, and it's got a dipole of 3.9. Okay. Notice it has a very high boiling point. All right, so that's about 125 C. All right, so it's high. Then let's look at propane, just for fun. It's got a molecular weight of 44, so the molecular weights are very similar, but it's got a dipole moment of 0.1, like almost none. And this boiling point is extremely low. It's going to be in the gas phase at standard temperature and pressure of 231 Kelvin. Pretty low. So anyway, that's dipole and induced dipole interactions. And we'll come back, we'll talk about some of the other interactions that we introduced earlier. So this is Coach Scott saying, have a great day, and holla baloo, connect.